Hello there and welcome to this first video in a series looking at GCSE Physics Revision, and we're going to be tackling the early stages of forces in this video. So the topics covered will be speed, velocity, acceleration, and then graphs and equations of motion. So let's look at average speed first. So this is the most commonly remembered equation by GCSE physicists, lots of prior knowledge from Key Stage 3 and stuff like that. So average speed is distance covered over time taken. And in physics, usually use meters per second. Well, we always use meters per second, really, in calculations, certainly at GCSE physics. We need to stick to those units. You can't reuse things like miles per hour and stuff like that because it just won't work. Also, in terms of different equations there, distance is equal to speed times time, and time equals distance divided by speed. Now, as I've said in another video, I devoted a whole video to learning how to rearrange equations. That is the number one skill really in GCSE physics, and the difference can be between 4, 5 and 6, 7, 8 and 9 grades, learning how to rearrange. So try and seek out that video if you need to work on rearranging equations. So speed conversions then. This slide just gives you some examples about how you can change units. So if you start off with 1 kilometer per hour, that's 1,000 meters per hour. But an hour itself has got 60 lots of 60 seconds, so 3,600 seconds in. So 1 kilometer an hour, if you want it in meters per second, you need to do 1,000 divided by 3,600. So it comes out to be 0.28 meters per second. Now, in most exam questions, you will have to change some of the prefixes, things like kilo, removing them, so multiplying by 1,000 to change into, say, meters from kilometers, that kind of thing, and that you gain marks in the exams by doing such things as that, and often making sure that the time is in seconds, not in hours or minutes. Just out of interest there, 1 meter per second is 3.6 kilometers per hour, and also just out of interest, not really important for exams, 100 kilometers per hour is around 63 miles per hour. Okay, let's get into some questions. So each time I have a question on the slide, you can pause the video and have a go at it yourself if you want. Okay, so have a go at that question using the equation we've just covered. Okay, so hopefully you've paused that and had a go at it if needed. So you take the equation. This is the easiest type of question where you don't need to rearrange the equation at all, and you don't need to change the units. The units are in the correct units, the SI units, the meters and seconds. So it's just 1,000 divided by 20, so 50 meters per second, which incidentally is about 120 miles per hour. But again, we're not using miles per hour. We don't tend to do that in physics. What about question 2 here? So going into the waves topic here, sound waves travel about 340 meters per second through air. How far will a sound wave travel in 1 minute? So if you'd like to have a go at that, pause the video now. Now that speed there is at about 20 degrees, something like that. It's about 330 meters per second at 0 degrees Celsius. Okay, let's have a little look then. So this time you did need to rearrange the equation, okay? So distance is speed times time, and the speed is okay because it's in meters per second, but the time is 1 minute, so that's not going to work in terms of units, okay? It needs to be in seconds, and so the answer there is 60 seconds, or that part of the question. And so the total distance is going to be the speed, which is 340, times 60, which is 20,400, or 20.4 kilometers. Now, just an aside here about why you have to use the right units. If you think the distance is in meters on the left-hand side, and if you take a look at the units on the right-hand side, they're meters / seconds times something in seconds. So the 2 seconds there will cancel. And so overall, the unit on the right is meters. Okay, so that's that way that the equations work, so that the units on the left-hand side are equal to the units on the right. If you did minutes there, then it wouldn't cancel. It would be a mess and it would be wrong. Okay, now for these tables, most of the time they start off fairly easy, and then usually the last line or two are a little bit more complicated, okay? So pause the video now if you'd like to have a go at that. Okay, so I'll just go through by putting the answers up on there. If you get stuck on any of these, just let me know. Just let me know in the chat and or the comments, and I can certainly help you there. But yeah, the last two there, you've got kilometers, then you've got minutes and seconds, sort of mixed units there. And then you've got kilometers again. You'd have to change to meters then in the last one. Okay, so hopefully you found that okay. Right then, let's have a look at how you display information about movement. So the two main types of graph for this topic are distance time graphs and speed time graphs. Now, speed time graphs tend to come up more often because there's more you can ask about a speed time graph than a distance time graph, if I'm honest. But let's cover this because they do come up still. So here's a graph here of an object moving in a sort of uniform motion. Distance time graph, so the distance there in meters on the y-axis and the time in seconds on the x. So the slope or the gradient of a distance time graph increases with speed. That's the first thing to say. Okay, so the slope. So if you had two objects, two vehicles maybe moving, you'd be expected to know that the blue line represents a faster object, okay, and the red line a slower moving object. And what this is all because the slope or the gradient of a distance time graph is actually equal to the speed. So if you think about the y step is the distance over the x step, the time, so distance over time is speed. So hopefully you can see the link there. So in the graph opposite there, if you take 150 on the y step, then divided by 10 seconds there, you get 15 meters per second. There is the average speed. And that speed doesn't change because the slope doesn't change. Some harder questions, the slope might change and not be a straight line. So the speed there was 15 meters per second. So let's have a go at some of these questions here. So it says to sketch on the same set of axes distance time graphs for a car moving at a steady speed, which it's a bit awkward the way it's displaying it here. I'd have to go through with the answer. And a bus moving at a steady speed that's greater than a car. So I won't pause that one, but it's just a steeper gradient essentially, okay, a steeper slope. And then lorry increasing in speed from rest. Have a little think about that one. See how you think that would be represented. The other two are steady speed. So pause the video if you want to think about that. But how you represent increasing speed would be with a curve, okay, which is a bit more complex and doesn't tend to come up that often in my experience. Okay, now they've got three lorries here, X, Y, and Z in the graph there in this question. And it doesn't really describe it properly here. What it wants you to work out is the speed of each of the three objects, okay, the three lorries. So there's one speed for X, one for Y, but you can work out three speeds for Z, okay, if you think about it, and what's going on in the middle there in that graph. So if you want to have a go at that, pause it. Okay, so what we'll have on the next slide is the calculations. So for X and Y, it's fairly straightforward. So you've got 4,500 or 45,000, sorry, divided by 1,800 is 25 meters per second. That's moving the quickest. Lorry Z going a little bit more slowly, 20 meters per second. Now for Lorry Y. Lorry Z, though, when it's moving at slowest, okay, from the early part of the journey, it's actually going at 16.7 meters per second. Then it's stationary for 600 seconds. And then from 1200 to 1800 seconds, it's going again at 16.7. So overall, it's the slowest, okay? But you could work out a third speed there. This is where the term average is important, okay? The average speed of Lorry Z is even slower because that takes into account the region when it was stationary. So make sure you read the question properly and when it's looking at this kind of thing. For Lorry Z, that type of question where you've got a stationary part as well, whether they're trying to work out the average, whether you're supposed to be working out the average speed or the speed between two different time points, okay? Because it's easy to make a mistake in an exam on that kind of thing. Just worth rereading the question. So let's move on to velocity then. So velocity of an object is its speed in a given direction. And I often use the words interchangeably throughout lessons and things like that, but they are different, okay? Subtly different. So an airplane there might do a loop-the-loop at a constant speed, but its velocity will be changing because its direction of motion changes. Now, in the next video clip in the series, we'll be looking properly at vectors and scalars, which is what we're really looking at here. So speed is a scalar. It's just a number. So 5 meters per second. That's a speed. But velocity could be 5 meters per second to the north, because you're given a direction there as well, okay? So the direction is changing constantly when the plane there is moving in a circle. So its velocity is changing, but its speed is constant, okay? But we will come back and look at that in more detail, looking at other variables that are vectors and scalars in the next clip, okay? So you got a stone dropped off the top of a cliff and falls down by 20 meters in 2 seconds. Calculate the average speed or velocity downwards and horizontally. So if you'd like to have a little go at that, pause the video. Okay, so its average speed downwards, because it would accelerate, right, would be 20 meters. So distance divided by time, 20 divided by 2, 10 meters per second. Okay, because it would start from rest and then it would accelerate. Now, horizontally, hopefully you've got that one to be 0, okay, because it's not moving horizontally, it's being dropped vertically downwards, okay. Bit of a trick question, really. Okay, now acceleration, we've hinted at that already, about change in speed, okay. It's acceleration is change in velocity divided by time taken. Now, you've got to be careful there to definitely include the word change in the equation. Okay, if you don't do that, then often in most exam boards you don't get the mark. If you put like speed over time or something like that, or velocity over time, you might not get the mark. Okay, so acceleration is change in velocity divided by time taken. And in terms of letters, you've got a equals v minus u over t. So little a is acceleration. That's fairly easy to remember. The bits that are harder to remember are the different velocities. So v is the final velocity and u is the initial velocity or speed, okay? And time t again is fairly easy to remember. But that's one of the equations of motion, really, that is called, okay? That a, well, it's sometimes written as v equals u plus at, which is a rearrangement of that. The unit for acceleration is meters per second squared, and that's something that sometimes causes problems, okay? It's because there's 2 seconds there, okay? And so you put s squared there, okay? It's nothing to do with squaring the answer. A few times over the years I see students get an answer for acceleration and then square the number. Please don't do that, okay? Because it's to do with the unit, it's not to do with the quantity, okay? So the final velocity there is in meters per second, the initial velocity or speed in meters per second as well, and the time in seconds, okay? So quite a complicated equation, really. Most equations in physics are sort of x equals y times z. This is a bit more complicated, a bit more difficult to rearrange. So there's a little bit more here on why it's meters per second squared, okay? So velocity change is meters per second, right, in the numerator. And then in the denominator, there's a seconds for time, okay? So you've got meters per second, okay? And you can put that all together and it looks a bit tidier as m slash or solid as s squared. Or you could do ms to the minus 2 to the power of minus 2, okay, which is the same thing. But that's an important point because if people do slip up on that, okay. So other notes then, often but not always speed can be used in the equation. You could hear me use the words interchangeably there. Change in velocity, remember, is the final velocity minus the initial velocity. And it's important you get it that way round, okay? Because you could get decelerating, okay? Or deceleration, where this is where the speed is decreasing with time. And then you get a negative answer, okay, in the previous equation. So if I go back here, or way back to the letters, if u is larger than v, then you're going to get a negative answer. So your acceleration will be negative. Or you could say it's a deceleration and just use the positive number, okay? But don't say a deceleration and then a negative number, because that would sort of cancel out then, okay? So try not to do that. And yes, circular motion at constant speed, acceleration is occurring because the direction of motion is changing, so the velocity is changing. To go back to that plane example earlier, okay? Because the velocity is changing, it is actually accelerating, okay? Which is not very intuitive, I don't think, at this stage. So here we've got a little question here. Complete the table for a plane accelerating at 8 meters per second squared. So pause the video if you want to have a little go at that. So here we are. There's the answers filled in. Hopefully that wasn't too much of a problem. Second question then, calculate the acceleration of a car that changes in velocity from 5 meters per second to 25 meters per second in 4 seconds. Now, with these questions, from now on, what I would try and do is write down the variables, okay, first, because there's a lot of numbers that you're given, okay. So you're trying to calculate a, so I'd probably put a equals question mark, and then it says from 5 meters per second, so that means that's the initial velocity or speed. So u is 5, v then is 25, and t is 4. And if you write that down, then that kind of method will serve you well with these kind of questions and in topics like momentum going forward, okay? So if you put all of the variables in, then you get 25, take away 5 is 20, divided by 4, 5 meters per second squared. So again, remember the answer is 5, and the unit's meters per second squared. You don't square the 5 or anything, okay? Right, let's have a look at this one. This one's a lot more complicated. Now you've got to calculate the final velocity of a train that accelerates. So give you the acceleration, gives you the time, and it only then gives you the initial velocity. You've got to work out the final velocity. So again, if you want to pause the video, have a go at it, but make sure you write down the variables, a equals, and so on. The other thing, as I said with this, is you need to rearrange the equation, okay? So if you multiply on both sides by t, then you get to this stage, and then you can rearrange the equation further to get v on its own, okay? Although it looks like they're just working out at here in the PowerPoint. So anyway, if you work out a times t, 0.3 times 60, you get 18, but that's v minus u, okay? So the final train velocity must have been 5 plus 18 because it was already going at 5 meters per second. It's a little bit messy, that slide. I think maybe I should rearrange or have a look at that again, really, that slide. I should really have written v equals a times t plus u and go for the full rearrangement there, okay? So 23 meters per second is the final answer there for that question. What about this one? So it already tells you it's going to be a negative answer, okay, that comes out of the calculator anyway. And I would use a calculator for all of these things, okay? You're always allowed to do that in GCSE Physics. So calculate the deceleration of a car that slows down from 18 meters per second to rest. Now, let's have a little think about these words. To rest means that it's going to stop. So the final velocity is 0. Sometimes students look at this and think, oh, they haven't given me enough variables to work the question out. Well, to rest is telling you that v equals 0. Now, in other questions, it might say from rest. When it says from rest, it means that the initial velocity or speed is 0, okay? So they are still giving you 3 out of the 4 variables here, okay? So have a little go at this by pausing it if you'd like. Okay, so in this particular equation or question, you don't need to rearrange the equation. So you've got 0, and you've got to be careful, as I said here, to write these the right way around. So it's 0, take away 18, divided by 3. So there is a minus sign there. So the acceleration is minus 6 meters per second squared. Or you can say the deceleration is 6 meters per second squared, okay? Just try not to carry over the minus sign for the deceleration because it's given really by saying it's a deceleration, not an acceleration. Okay, well done if you got that right. And this little one here is just a practice for making sure that you can use the equation properly and rearrange it. So pause it if you want to have a go at it. But in the meantime, we will flick through it. Okay, you do get a deceleration in that final one. Hopefully you got that one right if you had a go at it. So we'll have a look now at velocity or speed time graphs, okay? And as I hinted at earlier, these come up a little bit more often, I've found over the years, than distance time graphs. Now, the slope of a velocity time graph represents acceleration, so not speed as it did in a distance time graph. And one of the main things you need to do, if you see a graph in a forces question, is check what the axes are saying, okay? What is on the y-axis? Is it distance or is it velocity, okay? So in this particular example here, you've got 2 different vehicles maybe. One's got a high acceleration because it's steeper, and one's got a low acceleration. So the slope of a speed or velocity time graph is the acceleration, okay? And yeah, it's what I try and do in class is put a few axes on the board. I show then what straight horizontal lines mean, or straight diagonal lines on a distance or a speed or velocity time graph, okay? So, you know, a flat line on a distance time graph meant stationary, okay? Whereas a flat line on a velocity time graph will mean constant speed, okay? And a diagonal line on this one means acceleration, but a diagonal line on a distance time graph means constant speed, okay? And then you obviously get a bit more complicated with curved lines and so on, okay? So as it shows here, a constant velocity there would be a straight line, okay, on a speed or velocity time graph. Deceleration on this type of thing would be a downward slope straight line, okay? It does come up sometimes, or quite often actually. Now, when I was saying that you can do more with this, so you can calculate more, then you can look at the area underneath a velocity time graph, okay? And the area underneath a velocity time graph represents the distance traveled, okay? So shown there by the green shaded region. So that's something two things you can do. You can look at the slope or the gradient, which will give you the acceleration, and then you can look at the area underneath the line or graph, and that will give you the distance traveled. Okay. So let's have a little look at this question. Sketch the velocity time graph of a car accelerating from rest. So that's saying u equals 0 to 15 meters per second in 3 seconds, then remaining at a constant speed for 1 more second. So have a little think about that. If you want to have a go at it, pause the video. So there's our axes labeled there, okay? And so initially it's accelerating in the first 3 seconds there, so straight line, diagonal line going up there, and then for the last second, just a horizontal line, okay? Well done if you got that right. Now it says calculate the acceleration and the distance traveled after 4 seconds using the graph opposite, okay? So this is a typical kind of question that could come up in an exam, okay? So pause the video if you want to have a go at that. Now the main thing, first thing to look at here maybe is the acceleration, okay? So it's the gradient. So it's on the y step, you've got 12, then you've got 4 on the x step. And so 12 divided by 4 is 3 meters per second squared, okay? Then looking at the distance, it's the area of, in this case, a triangle, okay? Often, in more complicated questions, you can have trapeziums, which you could still use this. You can look at the area of triangles and rectangles to make it a bit easier, okay? If you can't remember the area of a trapezium, okay? So the area under the graph, in this case, is the area of a triangle there, half base times height, or base times height over 2, depending on how you've been taught. So half 4 times 12, okay, which is going to be 24 meters. So that's pretty standard for a question, but as I say, often they're a bit more complicated shapes, not just a triangle. We'll have maybe a triangle, then a rectangle, then another triangle going down when it's decelerating, okay? So let's have a look at this question then. Calculate the acceleration and distance traveled using the graph below. Now, notice here that the red line doesn't start from the origin, okay? So if you'd like to have a go at this question, pause the video. Now, there's quite a few mistakes can be made here. I might have to flick back and forth between the slides. So let's have a look at acceleration first then, okay? So y step. Now, some people might slip and think that the y step is 12 here, okay? But it's not. It starts at 4, so it's 12 take away 4, okay? And then the x step is simple enough. It's just 10 take away 0. So it should be 8 divided by 10. Hopefully, if I remember that correctly. Yeah, there we go. So 0.8 meters per second squared. Okay, so that's a common error there to put 12, not 12 minus 4, because, to go back, it doesn't start at the origin, okay, at the 0. Now, what about the distance traveled? Okay, so you've got two shapes there that we've handily already sort of highlighted. You've got a triangle and a rectangle there, okay? So you can work out either of them first and then add them up. Okay, so the area of the triangle, I think you're probably going to look at first. Let's have a look. Well, note the rectangle. The rectangle, if you have a look on the previous slide, is 10 times 4. And then the area of the rectangle is half base times height, so half 10, and again, times 12 minus 4, okay, which is 8. And so it's 40 plus 40, and it comes out to be 80 overall, okay, 80 meters. So that's, that's quite a tough question, and I've seen that kind of thing not done correctly over the years for the reasons that I've tried to highlight there. Now, this is a bit more typical of what comes up certainly in the exam board that I teach. So calculate the distance traveled over the 15 seconds and deceleration during the final 5 seconds there, okay? So there's the graph. If you'd like to have a go at that, pause the video. And we'll have a little look. Okay, so over the first 15 seconds, and so that's the whole of that really, okay? You can look at the area of the rectangle, the area of the triangle. So let's have a look at the area of the rectangle. It's 10 times 20, so 200. And then the area of the triangle is a little bit more complicated. The y step is 20, and the x step is just that final 5, okay? So 20 times 5, and then divide by 2, or multiply by a half, okay? So that comes out to be 50. So 200 plus 50, 250 meters. Okay, now let's just go back and have a little look at the final bit. So it asks you for the deceleration for the final 5 seconds. So it'll be at the moment it was going at 20 meters per second at the sort of 5 seconds before the end, and then it goes to rest. Okay, so putting that into the equation, you get minus 20 divided by 5 is minus 4 meters per second squared, but that's the acceleration, remember, okay? And because it was 0 minus 20, that really should put that down as the y step. 0 minus 20, or if you were using the equation. Because 0 minus 20 is minus 20. So remember, the deceleration is a negative of the acceleration, so we don't write minus 4 down. We just say the deceleration is 4 meters per second squared. Okay? So that's, as I say, quite typical there of questions that come up. Now, some courses I've got this final equation in. Okay, this is the second of the equations of motion. Quite complicated. Look in, it's v squared equals u squared plus 2as. Just double check whether it's in your course or not. If it isn't, then you could stop the video now, and I hope you've enjoyed this recap of this topic. Okay, and look out for future videos. But if it is in your course, for example, it's in the edXLI GCSE course, then please watch on. Okay, so this one is given in the exam. Okay, it's quite a complicated equation, even before they started, COVID regulations or COVID help and giving equation sheets and so on. Okay, so it involves a lot of squares. Okay, so quite difficult to rearrange, compared to most of the other equations, really. Okay, a lot of terms involved there. So the final speed squared equals the initial speed squared plus 2 times the acceleration times the distance moved. Now, what a lot of people, the hardest thing really here is identifying that this is the equation that you need to use. A lot of the time, students end up trying to use a equals v minus u over t, and it doesn't work because they haven't been given the time. Okay, so have a look here. You've given the distance moved, which in some courses is x, but in this particular case is s. Okay, if there's a distance involved and it's got speeds and acceleration, then the chances are you're going to have to use this equation. If it talks about a time, then generally you use a equals v minus u over t. Okay, so there's an example here gone through of this. Okay, dropping objects, that kind of thing. And as I say, the key is identifying that this is the equation that you've got to use. Okay, it can be used in lots of different ways, lots of different scenarios. Okay, always remember the square root at the end here. So if you have a look, this question on about a vaccine drop from a helicopter hovering at a height 200 meters. So s or x equals 200. The acceleration due to gravity is 10 in this case. In some courses, it might be 9.8. So that will make it a bit more complicated. Okay, so the AQA course, I think, is 9.8. Okay, so A equals 9.8 or 10. Calculate the speed at which it hits the ground. So the final speed. Okay, so you're trying to work out V. Okay, and we assume that U is going to be equal to 0. Okay, because it's hovering at the start. And then if you put those numbers into that equation, V squared equals U squared plus 2AS, then you get 0 plus 2 times either 10 or 9.8 times 200. So using the easier 10, you get 4,000 there. But that's equal to V squared. So you've got to square root 4,000, which comes out to be 63.25 to 2 decimal places, okay? Meters per second. So that's quite a complicated one, okay? Like I say, the main thing is to write the variables down, as I said earlier in this presentation, okay? If you're interested where this equation comes from, it can be derived in a few different ways. It can be derived from looking at energy considerations, okay? So looking at kinetic energy and gravitational potential energy, for example, okay? So I think we pretty much reached the end there of that one. So hopefully you've enjoyed that recap of these initial topics in forces. Please look out for future videos on other topics in forces and hopefully eventually covering the whole of the GCSE physics course. Take care.